Hey guys, welcome to lecture number 15 in Calculus 1. So this will be the final lecture from chapter 3, and we will be talking about the related rates, and we will see some applications of it. But also I would like to cover something about linear approximation and differentials. Well, I would say that I will not insist too much on linear approximation and differentials, since it won't be that relevant for the exam. But anyway, I would like to cover them as well. So let me start first with related rates and applications. We will see some real-world applications of derivatives. And let me just say a few words what this is all about. So let me write related rates and linear approximation and differentials. Okay, so we'll cover these three things. And let me start first with solving related rates problems. Just like I said, you will see some word problems, and we would like to use derivatives in solving these kind of questions. Anyway, let me start with the general situation. So the general situation is as follows. So step one, so what we would like to understand about that problem is, so step one is, well, when we have a real world situation, we would like to draw a figure if appropriate. And we would like, well, after we draw a figure, we would like to assign the variables, so assign the variables to the quantities that vary. The variables to the quantity that vary. Right? Another thing that we would like to do is to be careful, this is very important, so to be careful not to label the quantity with a number unless it never changes in the problem. So be careful not to label the quantity with a number unless it never changes in the problem. So let me stress this out. Never changes in the problem. And this is very important. And you will see once we do an application why this is important, not to label, not to jump in and label a quantity with the number. All right, now step two. Well, in step two, we would like to find a formula or an equation that relates the variables. So find a formula or an equation that relates the variables. Ouch. Okay, And we would like to eliminate unnecessary variables. That's very important. So necessary variables. And once we do this, let me just explain what do I mean by this. Well, some of these extra variables may be constant. So some of these extra variables may be constants. But also others may be eliminated because of their given relationship among the variables. So so others may be eliminated because of given relationship among the variables. Okay, and now finally, step 3. Well, when we have everything set up, we would like to see, well, which variable is constant, which one is not constant, and we would like to differentiate, and that's a very important word here. So differentiate the equations. So at this point, in the final step, we would like to take the derivative of these equations. And let me tell you something here. So, well, we will usually differentiate implicitly with respect to time. So let me stress this out. We will differentiate with respect to time. Okay, so these are the 3 steps that we need to take into account. So far, it's just the philosophy on how would we would approach such a problem. But usually this is what you need to do. But now, let me just tell you about this. So you have seen 3 steps so far, but now step 4, it will involve a specific situation. So let me just say this. So in case of a specific situation, so when we deal with this specific situation, let me add step 4, and here we will substitute this specific numerical values right, and solve algebraically for any required rate. Basically, what am I saying here is that we will solve the specific equation that we get for unknown variables, and after plugging in the values for known variables. Okay, I think this makes sense. So these are the, in fact, let me just say this. We solve for unknown variables after plug in the values of known variables. All right. So this is the philosophy on how we will solve. And now let's get to some specific situations. So let me start with some examples. And the first example that I have in mind is the following. So example, usually I decided to take some examples from the book. And the first example is example number 2 from the book anyway, from your manual, but let me just call it example 1. It's a very specific situation, and let me just say it explicitly. So it says the following. A person 6 feet tall is walking away from a street light, right? 20 feet high at the rate of 7 feet per second, right? So the question is, at what rate is the length of the person's shadow the person's shadow is increasing? So that is a question. Well, I want you to look at the question, and you, when you have such a question, you need to identify some keywords here. You see, well, we need to answer this question at what rate. When you see this keyword here, what rate, and also you will see it again here, rate. When you see the word rate, you always think of derivative, right? So basically something is changing with respect to time. So you will think of a derivative of a function of variable t, where t is the time. And also we would like, since we're asked at what rate is the length of the person's shadow increasing, so this is important here. All right, so let's draw a picture first, right? So we would like to comply with the general situation. We'd like to follow those steps. And first, before we even start thinking of the problem, I think it's better to understand the problem by just drawing a picture. All right, let's do it. So I'm going to draw the following picture. So here will be the sun. All right, this well, doesn't quite look like the sun, but I'm going to write here sun. Okay. All right. Here, so let me just say that the person is, this is the person. So here at the point A, and now you see when now we have the same person at B here, so oops. So it will be like this, and now here okay. So it will be something like this. Anyway, the picture is not the most fortunate picture that you'll see, but I think it makes sense. And now from here to here, we'll have, let's say, x1, right? Here we will have x2 and x3. All right, let's identify these. So the first thing, when you look at the picture, right, as you can see now, note that the length of the shadow increases as the person is walking away from the light, right? That's quite obvious. In other words, the length of A, right, will be less or equal than the length of B and will be less or equal than the length of C. So let's write this. Let me write it here. So note that, so that's the first crucial observation that I would like to point out. So that the length of the shadows, the shadow, sorry about that, it's one shadow. Anyway, increases, so that's the crucial word here. Increases as the person is walking away from the light. Okay, this is a crucial observation that I wanted to point out. In other words, what I would like to say is that the length of, in other words, the length of at A, at the point A, so let me say here, A, B, and C. So the length at A is less than the length at B, and it's less than the length at C. Okay, that's great. All right, now let's pick a general position. So, right, this is the general picture. Now let me look closely now. I would like to see mathematically what do I mean by this. So now let us pick a general position. Okay, and I'm going to draw another picture which will be very, very similar to this one here. So let me do it again. So again, I'll have here the sun. So this is the sun, right? Okay. Okay, and now let me just say this is A. So here the distance will be 20 feet. Right, this is what the problem said, right? And now at this point, let's just say here at C, here we'll have another point, let's say D, right? So the distance from here to here, let's say it's X, from here to here, it's Y, and right from, let's say, this point E, this is 6 feet, right? Okay, right. So these are this is given. So let's look at the problem again. It says that a person is 6 feet tall, is walking away. Okay. So this is the height of the person, 6 feet tall, right? So this is where the person is. Okay, now let's see what do we have here. So we will denote x. So x will be the length of the person's shadow, the length of the person's shadow y will be the distance between the person and the light. Okay. And now we know that y changes, right? It's quite clear as the person is moving, y is changing, right? So let's write this. This is important. So we know that y is changing. So y changes, let's say, over time t. Over time, this is important. And as a result, x will change, x also changes over time. So as a result, x changes over time. Okay. All right, now let's look at this. So let me denote the sun as the point B so that we can, now look at the picture now. You see, we have a right angle triangle. And now let's do some elementary geometry here. You see, we have this right angle triangle ABC, and the right angle is at A. And you know some trigonometric formulas in the right angle triangle, right? You know Pythagoras and so on. So let's see. So let's look at the triangle ABC. So triangle ABC. Okay, and with right at A, right? So let's look at this. Well, and we like to, and also I would like to say, so this is the angle. So this will be theta. Again, this will be theta as well. And we can write tangent of theta. So if we look at this triangle, you can find, so the angle ABC is the same as the angle DEC, right? Because these two triangles, CDE, right, as you can see them in the picture, is similar to the big triangle CAB or ABC, right? Since DE is parallel to AB. So the angles, the corresponding angles will be equal. So you can talk about the same angle, and we denote this by theta. All right, that's beautiful. Okay, so let's just write this. So tangent of theta, we're looking at this big triangle. So we have that tangent of theta will be what? Well, tangent of theta will be x plus y over 20, right? You know, it's the opposite leg over the adjacent leg, right? That's the tangent. The adjacent leg is the distance from A to B from the sun, right? And this will be 20 feet. So we have this relation. But now I would like to compute tangent of theta, but this time in triangle CDE, right? As you can see here, look at this guy here, is also right angle triangle, right? But now we can compute also tangent of theta, and this small triangle. So we'll have, let's put here triangle CDE, which is right at the angle D. And let's see, we have the following. So again, we'll compute tangent of theta. So tangent of theta will be equal to, well, it will be x over 6 this time, right? It's the adjacent leg, which is CD over, oh, sorry, it's the opposite leg over the adjacent leg. So as you can see, it's x. So the distance from D to the point C is x, and the distance from E to D is 6. So 6 fits. So this would be x over 6. Well, guess what? Now we can set these two equations, we can set them equal to each other, right? At one hand, tangent of theta is x plus y over 20, and on the other hand is x over 6. So this implies that x plus y, everything over 20, is the same as x over 6. And we can solve this if we want. So this will be a mathematical equation in terms of which relates x and y. And now we can write x in terms of y if you want. And once you do the computation, so this will imply that y will be equal to, and if I look here and if we do the computation, so this would be, so 6x, 20x, okay. Okay, so this will be y will be 3y is, okay. So it's 7 over 3 times x. So let's keep that in mind. So at this point, we are in a fortunate position. We obtained an equation which relates y and x. But also keep in mind that these two are functions in terms of the time of t, right? So the rate of change of y, so every time when you hear the word rate of change, you always think of derivatives. So rate of change of y, you always interpret this as the derivative of y with respect to t, to the time. Okay, so keep that in mind. Okay, and now this implies that, well, if you look at the equation here, this equation, let's call this star. Now we can differentiate in terms of with respect to t, and we will get that. So then we have that dy over dt will be nothing else than 7 over 3 dx over dt, right? It's just by differentiating star with respect to t. Okay, that's great. And now let's look back at the problem. So we're asked at what rate is the length of the person's shadow increasing? So the person is walking away from the light. At the rate of 7 feet per second. Right? So this implies, so dy over dt will be, well, since the person is at the 7, so this means that dy over dt will be 7, right? So we know this, and now we need the rate of change of the length of shadow. Let me write this. The rate of change of length of the shadow. In other words, what is this? So this would be, which is dx over dt. So we need to find this guy. Well, at this point, it's quite clear because we have this equation. Look at it. You see this one here? So now you just have to plug in dy over dt equals 7, and there you go. So this implies, so finally, we obtain that dx over dy, the dx over dt, sorry, this would be nothing else than, in fact, let me just write the equation so that you can see exactly how. So it will be 7, which equals 7 over 3 dx over dt. And from here, clearly it follows easily that, well, it's basically immediately, it follows that dx over dt is 3 feet per second. And that's it. Pretty simple, huh? Well, the only difficulty here is, I would say, is just to draw the picture to see which one varies, and then at the end of the day, just computing derivatives and plug it in stuff and solving algebraic equations. That's not, that's pretty much the problem. Now, let me give you another example. I'd like to, so this is the first example. Example number 2. Says the following. So let me, again, this is a problem taken from the book. Well, it's pretty standard problem, and it says the following. A bag is tied to the top of a, let's say, 5 meters ladder resting against a vertical wall. Okay, right. Now suppose that that the ladder begins sliding down the wall in such way that the foot of the ladder right? The foot of the ladder is moving away from the wall. Okay. Now the question is, how fast is the bag descending at the instant the foot of the ladder is 4 meters from the wall, and the foot is moving away at the rate of 2 meters per second, and the foot is moving away at the rate of 2 meters per second. Okay, so this is the problem. Let's look at it very, very carefully. And let's identify some things before we even draw a picture. Let's look at it. You see, I have a bag which is tied to the top of a 5-meter ladder, right? Against the wall of vertical line. So this is a 5-meter ladder. This is important to retain. And also the ladder begins to slide down. So we have a ladder, and it will begin to slide down in such way that the ladder is moving away from the wall, okay? And now we're asked, how fast is the bag descending at the instant foot of the ladder, right? When this is 4 meters away from the wall. And the foot is moving away at the rate, again, we have this word, a rate of 2 meters per second. So again, when you have the word rate, you always think about derivative, right? I think the picture starts to become, becoming a little clearer, I think. But let's draw a picture so that everything will be even clearer. Okay, let's look, so this is, let me draw the wall first. This is the wall. Right, so this is the wall. Right, and let's just say here we have something like this. So this is the ladder. Okay, we just draw it. And we also know that this guy is sliding. So let's just write here that so this is the wall and this is sliding. Well, let's keep that in mind. And here the distance will be, let's say, x. Okay, and we know that this guy, the ladder, is 5 meters. And now the distance from the ladder, so this guy will be y. Well, if you look at the picture again, we deal with the right angle triangle. But first, let's write down what we know. So we note that when the ladder is sliding, right? It's sliding down. The distance between between the base of the wall and the foot of the ladder is x, right? Equals x. And now the distance between the base of the wall and the top of the ladder is y. So, and also keep in mind that these two guys, x and y, are functions of time. So they're changing over time. So let's keep that in mind. X and y are functions of t, let's say. And they're changing over time. Okay, so let's keep this in mind. Now, okay, now let's look at the picture again. Just look at it. You see, what do we have here? So we have a right angle triangle. Let me just say that this is whatever you want to call it. You know, you can put here 3 points, let's say A, B, and C, right? The distance from A to C is x, the distance from A to B is y, and now you know that the distance from B to C, which is nothing else than the distance of the length of the ladder, is 5 meters, right? So it will be 5. Well, our good old friend Pythagoras says that the sum of the squares of the feet will be the square of the hypotenuse. So by Pythagoras theorem, so we have that, well, x squared plus y squared equals 5 squared, which is 25. And now keep in mind that these functions, again, these functions x and y are changing over time. So they're functions of t. So keep that in mind. So now when we want to differentiate, right, with respect to t, so let's do that. So differentiating with respect to t, gives us the following. So we will have that 2x dx over dt plus 2y dy over dt will be equal to 0. So this is what we will call the general situation, right? So as you can see, we took the derivative with respect to t. And now, so this is what we call the general situation. And now let's see what happens in our specific case. Let's look back at our problem and let's see. So our specific situation is the following. Well, let's see. So the specific situation, so we know that, well, the rate of change of x is 2 miles per second. Look at this. And at this time, x will be 4, right? If you look at the question, it says, well, how fast is the bag descending at the instant the foot of the ladder is 4 meters from the wall, and the foot is moving away at the rate of 2 meters per second. So we can identify here that x is 4 meters, right? And dx over dt is 2 meters per second. So our specific situation, so the rate of change of x is dx over dt, which is 2 meters per second. And at this time, x is 4 meters. Okay. And now what we need to find, so we need to find the rate of change of y, which is nothing else which is dy over dt. So we need to find this guy. Well, so we need to find this, knowing this and knowing this. So let me, so we need to find dy over dt at this time. Okay, I think the picture is quite clear at this point. So we just need to, let's go back to our equation. You see, we have 2x dx dt plus 2y dy dt equals 0. So now we just have to plug in x equals 4 and dx over dt equals 2. And we can find dy over dt. So let's do that. So we have 4 times, so 2 times 4 times 2, right? Plus 2y dy over dt is 0, or equivalently, this will give us that dy over dt is nothing else than just negative 8 over y. So we will have this. But now the question is, how do we find y? So the question is, how do we find y? Well, again, our good old friend Pythagoras, so we'll go back to our initial equation, you see, x, you see this one here? Look at it. So this guy, when we plug in x equals 4, we can find out y. So we go back to our initial equation. So going back to the initial equation, we have so in fact, let me write it this way. X squared plus y squared equals 25. We have 4 squared plus y squared equals 25, which will give us, so from here it follows that y squared equals 9, and well, y will be plus minus 3, but y has to be positive, so it will be only, we'll retain only y equals 3, right? So finally, this will give us dy over dt is negative 8 over 3 meters per second, and that's it. That's the problem, right? You see, a very similar situation again, Pythagoras. Now let me do another problem, and so another example. Example number 3, I think. Okay. Okay, let's see, example 3. And now we're going to talk about, since I'm in Los Angeles at this point, so why not talking about the flight to LA? So the problem says the following: every day, a flight to Los Angeles flies directly over my house. I wish, anyway. At a constant altitude of 4 miles. Okay. If I assume that the plane is flying at a constant speed of 400 miles per hour, right? Now, at what rate, right? So at what rate is the angle of elevation, of my line of sight, right? Changing with respect to time, when the horizontal distance between the approaching plane and my location is exactly 3 miles. Wow. You see it like a real world situation is exactly 3 miles. Wow, you would never guess that this problem would use derivatives, right? All right, let's look at some keywords here. Again, when you see the word rate, you always think about derivatives, always. And now let's look. So we have this flight to Los Angeles, which flies directly over my house at a constant altitude of 4 miles. This is important. And so we have the plane is flying at a constant speed of 400 miles per hour, okay? So altitude is 4 miles, and the constant speed is 400 miles per hour. This is important if the speed is constant. And now we're asked to see at what rate is the angle of elevation of my line of sight changing with respect to time, when the horizontal distance between the approaching plane and my location is exactly 3 miles. Okay, now let's draw the picture so everything will be very clear. Right, so now let's look. Okay, so let's draw the picture. So I'm just gonna, so here what the plane is. Oh my God, I'm gonna draw a plane. It's not my, okay, imagine that this is the plane. Whatever. Ouch. Okay, so this is the plane. Right, so this is the plane, right? Okay, now let's see. So so the distance, we said that the altitude is 4, and this is the line of sight. Right. Okay. And this is the angle of elevation. This would be right, the count. Yeah. So this would be theta, which will be the angle of elevation. Then this will be x. And the line of sight, we know from Pythagoras, is nothing else than just x squared plus 4 squared. Right? The good old friend Pythagoras. All right, so this is the picture. Look at it. And now let's see, what can we do? So the angle of elevation, let's write this. the angle of elevation as theta. Look at this guy here. Okay. And now let's see, how can we find theta, because we're interested in this. Well, the only thing we can do here, right, you see we have x, we have 4, and now if we take the tangent of theta, this is a right angle triangle here. And if we take the tangent of theta of the angle of elevation, that would be the opposite leg over the adjacent leg. So this would be, let's write this, tangent of theta will be 4 over x. And let's keep this in mind. Okay, so this is the relation, we want to keep this in mind. And pay attention that this will, this is also x, and theta will be, these are functions of variable t, so they depend of the variable time. And now we will take the derivative in this expression. So by taking the derivative, it follows that d over dt of tangent of theta, we're going to take the derivative with respect to t, and this would be nothing else than just the derivative with respect to t of 4 over x. Keep in mind that both of these two functions are of variable t. I'm not just going to write it, but I assume this. So this would be equivalent with, let's see. So the derivative of the, so we will apply the chain rule here, right? We have the tangent of theta of t. So this would be the tangent of the derivative of the tangent will be the secant squared. So this will be secant squared of the theta times d theta over dt, which will be equal to negative 4 over x squared dx over dt. Right? And now we can isolate this. So this would be equivalent with d theta over dt equals negative over x squared secant squared of theta dx over dt. Right? Okay, that's great. And now, well, let me just remind you the fact that secant squared of theta is nothing else than just 1 over cosine of theta, right? And this guy, if we write, is nothing else, cosine of theta, by looking back in our triangle, cosine of theta will be what? Will be 1 over, so cosine of theta is x squared over x squared plus 4 squared, which is 16. And this would be nothing else than just x squared plus 16 over x squared. Okay, so we know secant of theta, so we can plug it in. And this will give us this gives us that the theta over dt will be, and now just let's replace, so this would be negative 4 over, so this would be, yeah, so it will be negative 4 over x squared plus 16 dx over dt. All right, so this is the general situation we have at this point. And now let's see, what specifics do we have? So this is the general situation. And now let's look back at the problem. So the specific situation is that, let's go back. You see, we assume that the plane is flying at the constant speed of 400 miles per hour. So this means that dx over the dt is, well, since it's flying on the opposite direction, it will be, so we know that So the specific situation, and this is very important. I want you to be to pay attention here. Dx over dt is negative 400 miles per hour. And why is that negative over there? This is an important question. Well, it's because the distance is decreasing. That's important. That's why we have this negative sign here. Keep that in mind. If the distance was decreasing, then we would have had plus, right, 400 miles per hour. This is very important. This is very tricky. So that's why you need to pay attention to this detail. So when we, again, when we have the negative sign, we know that the distance is decreasing. Okay, now we know dx over dt, and now what we need to find, so we need to find d theta over dt at x equals 3 miles. Okay, so finally we have d theta over dt equals -4, and now so it's 9 plus 16, right? 3 squared, which is 9, times -400. Well, and this will give us, if you do the computations, would be 1,600 over 25. So this is approximately, if we look, something around 64 radians per hour. So that's the angle of inclination. And that's it. So these are the 3 types of examples that you will find in some word problems, right? Anyway, I'll do more examples when we'll have a review session before the midterm exam. And now I'd like to veer towards something else, and I'd like to talk about the second part of this lecture, and this will be devoted to linear approximation and differentials. Right? All right, let's see what this is all about. Well, let me start first with the tangent line approximation. Well, here, if a function f of x is differentiable at x equals a, right? Then the tangent line so then the tangent line at a point a equals f of a, right, on the graph of y equals f of x, right, has the slope, so has slope. Well, the slope, as you know, this is nothing else than just the derivative at that point A. So let's denote this M is f prime of A, right? And the equation, so has slope, an equation. In fact, let me, and the equation will be y equals f prime of A, right? Plus times x minus A plus f of A. Okay, so we already knew this stuff, right? So this is what happens with the tangent line at a point, right? Of the graph of f. Okay, but now if x1, let's say, is near the point A, right, and then f of x1 must be close to the point on the tangent line right to y equals f of x at x equals x1. And that is, so we will have the following approximation, and I'll write it in this way. So we'll have that f of x1 is approximately f of A plus f prime of A times x1 minus A. All right, you will see that this will look similar to some other stuff that we'll cover in chapter 4 when we will talk about the qualitative properties of differential functions. And you will see that this will be somewhat related to what we will call the mean value theorem. But anyway, hold your breath, we're going to get there. Let me draw the following picture so everything will be a little bit clearer. So let me just draw. Okay, now let's say we have here the point x1 and f of x1. Okay, so here, let's just say here I have the point A, and this is f of A. All right, let's just say here is the point P of coordinates A, f of A. And here, let me just say we have x2, and this will be f of x2. Right, and now let's just say that the curve, so the function f will go like this. So let me just draw it with red. So the curve will go ouch. Okay. So let me just say that the curve will go like this, right, through P, and it goes like this. So that's the graph of f, right? So this will be tangent to this point P of coordinates A, f of A. And now, but also when we draw the tangent line, so let me just draw it, the point P, look at it here, it will intercept, let's say, here and here. So this would be the point of coordinates f of A. So here we'll have f of A plus f prime of A times x minus A, x1 minus, sorry, minus A. And here we'll have f of a plus f prime of a times x2 minus a. Okay, right? This is the picture, and we will refer to this as the linear approximation of the function f at the point x equals a. So we refer to this as a linear approximation of f of x at x equals a. And now then this will imply that the function, and we will write this function in the following way: L of x, which will be what we will call the linearization of f. So this would be f of a plus f prime of a times x minus a. So this function that you see is called, this function will be called a linearization So this will be called a linearization of the function f at a point x equals a. All right, now let me point out a remark. So this is what we'll call the linearization. So keep in mind that L of x is nothing else than f of a plus f prime of a times x minus a. All right, good. Now let me point out a remark. Well, when the tangent line is close to the curve, it gives a better linear approximation. It gives a better linear approximation. Okay. Well, let me just draw a picture. So the picture is the following. So let's just say we have the graph goes like this, right? And let me just say we have something like this. Now here we have the point, and this will be the tangent, right, at this point. Okay, so the linear approximation for x1 will be a good approximation but for x2 will not be that good. Anyway, let's see some examples. Example 1. Let's see some a couple of examples of how these things work. For example, find the linear approximation around the point x equals 4 if the function is f of x equals the square root of x, right? And we would like to use this approximation to evaluate let's say the square root of 4.36. Okay. So you know what the linearization function is, so we should come up with that. The linearization of f right at a point x equals a, at x equals a, is given by what? It was L of x was f of a plus x minus a times f prime of a. And now in our case, the point a, in our case, a equals 4. So now let's compute these values. As you can see, it's pretty straightforward. So we have that f of 4. Well, keep in mind that our function is the square root of x, so we'll want to find the linearization of this guy. So f of 4 will be what? Will be square root of 4, which is 2, right? And we also we have to compute the derivative of this guy, and we know that f prime of x is 1 over 2 square root of x, right? The derivative of the square root of x. Well, and f prime of 4, right? We will plug in x equals 4, will give us nothing else than just 1 over 4. So finally, the linearization function L of x will be 2 plus, so f of a is 2 plus 1 over 4, which is f prime of a, times x minus 4. So that's the linearization function. And if we do some computations here, a little bit of algebra, this is nothing else than just 1 plus, well, x over 4. Okay. And now we would like to evaluate. So when we want to evaluate the square root of 4.36, this would be, we take x equals 4.36. So the L of 4.36 will be 1 plus 4.36 over 4, which is 1 plus 4.36 over 4 will be 1.09, which will be 2.09. And that's it, right? You can also use a calculator if you want, but you'll see that using a calculator, it will give you a very similar value, probably 2.0899, whatever. Basically, it's the same thing. Okay. You see, that was the linear approximation around around the point x equals 4. Now I can also give you the linear approximation so the question is, what about the linear approximation? What about the linear approximation around another point? Let's say x equals 9. What about that? Well, you can do the same thing. The only difference is that you will plug in x equals 9 instead of x equals 4. And basically, you can evaluate the square root of 4.36, and the linear approximation will give you something like 2.22, something like this. So you see, the question is, well, I'll leave this to you as an exercise to figure out the details, right? Basically, you just mimic the same procedure. The only difference is that you will plug in x equals 9 instead of x equals 4, but the rest is identical. And you will get that, we would like to compare the two linear approximations, and you will see that the linear approximation of x equals 4 is much better than the square root of 4.36 than the linear approximation of x equals 9. Anyway, you will see that. You can just check by a computer as well to see that. Okay, now the last thing that I would like to talk about before the end of this lecture is, well, I think you got the picture of what's going on with the linear approximation, but now I'd like to talk about the differential a bit, especially when I will be dealing with this when we will talk about integrals. You'll see we'll have an integral, basically that will be in chapter 5, and we would like to compute the area under the graph of a function. You'll see that we'll deal with this integrals, and the differential will play an important role. But let's see, what is a differential? So we know at this point that, and let me say this again, because you will always you have seen dy over dt, dx over dt, but we know that dy over dt, well, we say dy over dt, but this is not the quotient of dy by dt. This is not the quotient of dy by dt. Right? Keep this in mind. This is very important. Okay. But what do we mean by dy and dt separately? So the question is, what do we mean by dy and dt separately? Well, this is what we mean. So dy is the differential of y, and dt is the differential of x. So let's write this. The dt is the differential right of the of x, right? So dx is the t here. So t is the independent variable equal to delta x. So it's basically the change in x. So the change in t. Okay, that's what we need to know. And clearly, the dy is the differential of y, which is nothing else. Well, we will, when we have this, you know, okay, all right. So and here we'll have that this is the rise, so dy will be nothing else than the rise of the tangent line right relative to the same change in t, to the same change in t. Okay. So here you can say that we will have something like like dy over dt here will be nothing else than y prime of t, right? So this is how we denote this. And now let me see an example, a quick example of how to compute the differential. So we would like to find, let's say, d of x squared sine of x. What is this? And now let's see. So you can see here, we have the product of two functions. So we have that d of x squared sine of x is x squared d sine of x plus sine of x dx squared, which is equal to x squared times cosine of x dx plus sine of x times 2x dx. Or if you want to write this, if we factor here, so this would be x squared cosine of x plus 2x sine of x dx. And that's it. Okay, I think that's pretty much what I wanted to cover. I think I'm gonna stop here. This sums up everything we for chapter number 3. Like I said, we will start next week, chapter number 4. For the midterm exam, all the material up to chapter number 3, including chapter number 3, that will be part of for the midterm. And I will not include anything from chapter 4 that I will start doing starting next week. I'll do a couple of other videos. And that's it. Thank you very much.